and today we get to talk about the basics of synchronization. Okay, threads review. Look, I'm not going to go through the slides in this section because you've already seen them. Okay, threads are one of the two models we've talked about to allow for concurrent programming. One of the models we've talked about has been processes. Create new processes. Now you have concurrency. Parent does one thing, child does another thing. Parent does one thing, child A does something else, child B does something else, child C does something else, right? Now we have a whole bunch of processes all working collaboratively. The other model we had are threads. It works essentially the same way. We say we spawn a thread instead of forking a process. We say we join a thread instead of waiting for a process. There's some subtle differences, but the big difference, I guess the big differences, right, are the overhead is a lot less for a thread than a process. Because threads share the same context, right? Threads share the same virtual memory. They share the same file descriptors, the same signal handlers, right? All of that good stuff that's part of the process context. They share that. What they have are their own unique stacks and their own unique register contexts. Okay? And so when we switch from one thread to another, we restore its register context, right? Which restores its use of a particular set of, which restores its use of a stack. Because now I'm pointing at the right stack. Okay? So this is great in the sense I don't have to create a new process. It's great in the sense that I don't have to destroy a new process. I just sort of allocate a new stack and some data structures representing the register context, and I'm good to go. And when I'm done, I just basically clean up the register context. Great. But it also complicates things a little bit, because now I have sharing. All of my threads exist within the same virtual memory. So they all share the same virtual memory. So they all share everything at some level. They all have access to the entirety of that VM. Now, it may be the case if things are going correctly, one thread uses its stack, another thread uses its stack, another thread uses its stack, and they all share the global variables and things like that. But of course, it's also the case that if something goes wrong, one thread has really deep recursion. It can run over another thread. Or one thread's logic is bad and has a bad pointer. It can write over some global data structure or another thread stack. Right? So at one level, there's the way it should work, and then at another level, there's what happens when the model breaks down because we have a bug. And that's really rough, right? Because the point in life we don't want the model breaking down is where we have a logic error. Because now we have two problems, right? We have the original logic error, and then we have the side effects of that logic error. If one thread overwrites another thread's stack, my bug is going to may well appear in the second thread, right? When that thread tries to return to a bad stack frame, a corrupted stack frame. So now I'm debugging the wrong thread. Why is this thread exploding? Why is this thread getting a segment violation? It's getting a segment violation because the return address is bad. Well, how's it managing that? Some different thread, right? It's complicated because we have to think about it a little bit. Sometimes the sharing is great. If I want multiple threads working together and they share state information, that's fantastic. Of course, it's not so much fun if I need to think about things like, I have one copy of this variable, and this thread wants to use it, and this thread wants to use it, and those are different uses. Think about our threaded web proxy. Right? Remember, we had to malloc a new file descriptor each time, right? Every time we accepted a new connection, it needed a new file descriptor. We had to do that in the threaded version, but not in the forked version, because fork naturally provided that copy. Threads, there was a file descriptor, they both shared it. So if I wanted one for you, and 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 one for you, we had to malloc that. And that might be easiest to remember, but there was the other problem, which is what did we have to do with it? If we malloc it, we must free it, right? And that was a pain. Because we malloced it on the server side, right? The main front-end thread, and we had to remember to free it in the worker thread. So the sharing model can get a little crazy. And of course, once we start sharing things, as we might with threads, or we could with processes in some cases, now we have to worry whether or not our sharing is safe. Some things can be easily shared. We're all sharing the air in the room. We're not fighting over our share. Right? Not a big deal. You're all sharing the screen. Right? Everybody's sharing the same screen. We're all looking at the same screen, right? No problem. Of course, sometimes sharing is a problem. We already talked about this. No one's going to share a toilet. That's just not going to work, right? So that's what this set of slides gets at. Remember, threads have their own stacks, and they have their own register context. When we switch from one thread to another, we restore the register context, so now the stack pointer and base pointer are pointing at the correct thread. Some people call it a thread context switch. It's really a thread register switch, or simply a thread switch. We're really not changing the process context. Call it the thread context if you want, but remember, we're not changing the process context. We're not changing the virtual memory or signals or files or anything like that. Come on, put your cell phone away. Busted. Okay. The thread library we tend to use, and there's a little red P written next to threads. Look, you can create a thread model of any kind you'd like. Right? There's no trademark on threads. There's no international body for a thread standard. So to some extent, you could create some model for parallelism and call it threads. I mean, Georgia Tech created a curriculum model and called it threads. Right? Whatever, okay? The model we're talking about, as threads is pthreads or POSIX threads. It's a particular standard for threads. Okay? In pthreads, each thread has its own logical control flow. In other words, each thread lives its own life, calls its own functions, does what it wants to do. Each thread can run concurrently with others. If you have a multi-core processor, you can have one thread on one core, one thread on another core. If you have a single core processor, they can interleave. They're separately schedulable. Each is switched. I don't run one thread to completion, then run another thread, at least not necessarily. They're interleaved. We have concurrency even if we don't have true parallelism. Threads and processes are different in that threads share code and data. Processes typically do not, right? The whole point of having a process is protection. If I fork, it's copy on write. I can't change your data. Of course, vfork write can change that a little bit, but threads are less expensive since they don't have all that machinery, since they share that machinery, right? Threads are just cheaper to create and destroy. Since we're not doing a true context switch, we're not changing out, virtual memory. Switching between threads is just much faster. So when we're sharing, right, we have multiple threads existing within the same memory context, right? They're sharing things. So the question is, which variables in a thread C program are shared? In our logical, pretty view of the universe, the answer is threads share the text area and globals. They don't share their stack, which means they don't share the local variables. Right? That's the simple, pretty picture. Now, we can get in some technical cases, like what about a static local variable? Is that shared or not? Somebody tell me, what is a static local variable?
Basically the same as a global.
Okay, it's basically the same as a global. So when would I use a static local variable?
When you're trying to get around a restriction that you can't use a global.
Okay, when I'm trying to get around a restriction, I can't use a global. Maybe I'll buy that. But somebody tell me, where is a static local variable declared?
You use it when you want it to have local scope, but you want it to stay the same as long as the process is alive.
Okay, the typical way this is explained is exactly that. You typically, the way it's typically explained is you use a static local variable when you want a local variable, that is to say a variable that is within some function's namespace and can't be accessed outside of that function, but has a lifetime beyond the lifetime of the activation of that function, of a single function call. So it lives from function call to function call to function call. Okay? So a local variable that's remembered between calls. Static local variables, basically, right, are global variables that are like global variables, but they're local namespace. So they're declared with other global variables. They're not declared, they're allocated with other global variables. Okay, so when you declare a static local variable, it's not on the stack, because the stack would go away when you returned and moved your stack frame up to higher addresses, right? Instead, it's allocated with global variables. It's just the compiler knows that its namespace is not global. Okay? Lifetime is the lifetime of the process rather than the lifetime of the function activation, but the namespace is local to the function. So static local variables, because they're in that, that global data part, are actually shared among threads. They're not in the stack, which is duplicated. They're in the global space, which is not. So, you know, the simple answer is things on the stack per thread. Things not on the stack, global. And that's a great answer. 99.5% of the time it works that way. Then there's that 0.5% of the time. And that's when life sucks. That's when life sucks bad. Right? Because that's where your model breaks down. That's where you're in a situation where, even though normally each thread is playing nice and staying within its own stack, some thread has managed to screw up another thread's stuff because there's no protection. So it's got a bad pointer and writes on another thread's stack. Or it's grown too much and keeps growing until it writes on top of another thread. But in some way, shape, or form, one thread of control destroys another thread's stack or destroys some global state. And now, whatever other threads might look at that global state or use that corrupted stack end up having a hard time. They're chewing on bad data. It may cause a segment violation, right? Seg-V. May cause some other type of error. Or it may just cause bad results. Oops. Okay. So, you know, the next thing the slide says is to answer the question which variables in a thread C program are shared requires answering the question, what is the memory model? How are instances of variables mapped to memory? How many threads might refer to each of these instances? And it offers this definition. A variable X is shared if and only if multiple threads reference some instance of X. Okay, in other words, it's only fair to say it's shared if it's shared. If more than one thread of control is accessing it, is able to access it. Okay, so we talked about the conceptual model. Things on the stack, not shared. Everything else, shared. We talked about it not being strictly enforced. Any thread can read and write the stack of any other thread. So this mismatch between the conceptual model and the operational model is a source of confusion and errors. Right? If you're trying to debug and some thread, gives you a wrong result, you're probably debugging the logic for that thread, not realizing it's a case of garbage in, garbage out. Some other thread destroyed its data. Now it's suffering indigestion. Okay, here's an example. We have this function called main, and inside main stack frame is a variable called I. Okay? We also have a true global pointer called pointer. If you look at the thread, right, there's a static inside the thread. In other words, all threads are sharing that static, right? It may be local, but it's a static local. So if one thread increments it, all the rest of the threads are going to see it incremented. There's only one of them. And so we see that inside this thread, which has its own static local, it's getting its arguments, and its argument is going to be an integer, my ID. Okay? This integer, I, the ID, is part of that global variable. Now imagine this. Imagine that I spawn a whole bunch of threads. I pass in 1, 2, 3, 4, 5. Now I'm passing this I by value, right? So that I is going to be okay. Do we all agree? Because the I here is the variable that's local to main. The calling convention to C is passed by copy, right? Passed by value. So it copies that into the variable called varg_p. And now this function, right, this activation of this function has in its stack frame a copy of the variable I. So I'm okay there. You're going to be 1, you're going to be 2, you're going to be 3, you're going to be 4, you're going to be 5, you're going to be 6, you're going to be 7. There's nothing messing up there. Because each thread is being given a copy. It's being a copy by virtue of the function call, copying it from the variable I, right, into the stack. Just as functions do. Okay? So it's going to know its thread ID just fine. But they're all going to share this common count. Okay. This is sort of cool because what we're trying to do here, looks like to us, is to count the number of threads activated. So every time a thread runs, it does ++ count. Now many of you in your code have written count ++. What happens in C when you put the ++ first? What's that?
Increments before it does the rest of the operation.
Yeah, increments before it gives you the value. Right? Because I++ or ++I are both expressions. They both have values. Okay? So I++ has the value of what I was before the increment. ++I has the value that it has after the increment. Okay? So here you can see that we're just incrementing count. So sort of philosophically what this is trying to do is count the number of threads activated. But where is I? They're all sharing, where's count? They're all sharing the same count, right? So think about that. In order to increment a value, I need to load the value. So now I know it's 5. Then I need to increment the values. Now I know it's 6. Now I need to store that value back, so now I'm storing back to 6. Move it to a register, increment the register, move it back to memory. 3 operations. Oftentimes thought of as a load, an update, and a store. In this case, it's a move, an increment, and a move. Okay? So if you move the value of 5 into your register, and then it's his turn, and he moves the value of 5 into the register, and then it's her turn, and she moves the value of 5 into her register, and then your turn, you move the value of 5 into the register. And then you run again, and you make it 6, 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 and then you store a 6, and you store a 6, and you store a 6, and you store a 6. Do we have a problem? Yeah. We should have said 5 becomes 6, becomes 7, becomes 8, becomes 9. Instead, everybody incremented, but everybody wrote back a 6. Do you see the problem? Right? So there is this thing called a critical value. Critical variable, sorry. Okay? And count is it, okay? Count is a critical variable, and the reason it is because it's shared, but it can't be shared. It's shared, right, but isn't really shareable. It has to be protected. And this line of code here, ++count, is the critical section. Okay? We call it the critical section because it's the code that manipulates the critical variable. Make sense? Count is a critical variable. It's shared by multiple processes, but can't intrinsically be shared safely. ++count is a critical section of code. It's code that manipulates the critical variable in a potentially unsafe way. So that's what we have to look out for, right? When we're writing code, we look for what is shared. Is it naturally shareable like a projection screen, or naturally not shareable like a toilet? If we have a toilet that is shared, this is a concern. We need some mechanism to ensure that the toilet is used properly. One person at a time, right? A lock. So when we find a critical section of code that's manipulating a critical variable, we ask ourselves, okay, what can we do to make this safe? What can we do to protect this variable to ensure that it's being shared in a safe way? Some type of barrier, some type of lock, right? Very common answers. And we'll talk about how that's done. Okay. More generally than a critical variable, right? Sometimes the more general term is critical resource. Okay, it doesn't have to be a variable. It might be a printer. It might be a network connection. Okay? So the general process here is to find the critical resources, things that might be shared but aren't shared safely, find the code that's manipulating them, and see if there is concurrency, and then do something to ensure that that code respects the needs of that resource and ensures that if it's being accessed concurrently, it's being accessed concurrently in a safe way. In this case, our critical resource is the variable count. Okay? The critical section of code is the code that moves the value of count from memory into a register, increments the value of count, and then moves the value back from register to memory, represented here by ++ count. That section of code can't be interrupted. If that section of code is interrupted, we have an unsafe situation where you're loading a value and you're loading a value, right? So we need a way of mechanism for protecting that, for ensuring that that critical section is not allowed to be interrupted. Okay. We've already talked our way through that. I guess the one thing we didn't talk about is my ID is obviously a local variable, right? And so there's one per stack frame. Each thread has its own stack frame, so each thread has its own. Okay, we've talked our way through this. Okay. Now, I is a critical resource, right? I'm sorry, count is a critical resource. Count ++ is the critical section. So we have to ask ourselves, how can I be shared? I can be shared such that there's only one user at any point in time. Okay? That's how it can be shared. So a policy that can ensure this is what we call mutual exclusion. Mutual exclusion. All of the potential users of this resource mutually agree that if any one of them is using the resource, the others will respect that and not. Does that make sense? So the use by one, by mutual agreement, the use by one excludes use by the rest. So you can imagine what we're going to add here, some type of primitive that lets me claim this, mine, that everyone else will respect. And then a way of giving it back, done. So you might imagine that there is a single instance of a token. And if you acquire the token, the resource is yours. And when you're done, you can give the token back. And now somebody else can claim it. Does that make sense? So it's acquire, which is where you get it, and then it's release, which is where you give it back. Mutex acquire, mutex release. Okay? So we have a variable, a mutex variable, that represents this. Okay? The right to access the resource. If you acquire the mutex, you can access the resource. If you don't have the mutex, you cannot. Okay? Some people like to think of the mutex as if it were a key. I can use the resource if I have the key. No key, I can't have access to the resource. Make sense? Okay. So the way this usually works is there is a library that provides for mutexes. You initialize a mutex variable. A mutex variable is a variable that represents the right to use the resource. And then you call mutex acquire. If you want to use the resource, you call mutex acquire. That is a blocking call. Put your cell phone away. you call mutex acquire. That is a blocking call. You call mutex acquire, and you block. No, more like this. You block until you get the resource. When you call mutex acquire, you have the mutex, and that means you can use the resource. When you're done, you call mutex release, and now the resource is up for grabs. If no one's waiting for it, that's okay. It's up for grabs. The next person can grab it, mutex acquire, and go. If somebody else is waiting, maybe there's a queue. Okay? Somebody else now gets to go. I said maybe there's a queue. Because in the classic definition of a mutex, there's no guarantee that it's going to be first come, first serve. Okay? Somebody could get the resource before you, even if you've been waiting longer. And this is a little beyond the scope of 213. I'm just going to mention it in case you're curious. Generally speaking, there are two ways mutexes are implemented. Okay? One way is by what we call a spin lock. A loop, where I basically ask, do I have it yet? 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 Okay? Spin. Okay, that's burning CPU. Another way is with the help of a scheduler, where if I'm looking for the mutex, if I call mutex acquire, it sees if the mutex is available. If it is, I get it and go. If it's not, I get put over in some block queue. I am not schedulable, I am not runnable, I'm just hanging out. And I stay hanging out, leaving the processor and other resources free for other threads or other processes until the resource is available. Then I get made runnable, and eventually I run. And I'm able to grab the resource. At least I can look to see if the resource is available with a good reason to believe it will be. If not, because I was stuck in some queue and you actually showed up and grabbed it, I have to go back to the penalty box. Not fair. Okay? So because of that, because if we're just sitting here spin locking, the processor thread that's going to get the resource is just the one that happens to be spinning when it's free. There's no queue to that. It's just luck. And because even if I try to queue it, it might be ready, it might be my turn, I might be moved from a block queue to the runnable queue. Because of the scheduler, I may not get to run, and somebody else may just show up and take it. So although it often seems like first come, first serve, right? Technically speaking, there's not that guarantee. It may be totally unfair. Okay. So that's the classic semantic. That's the classic semantics of mutex. Initialize the mutex, acquire the mutex, release the mutex. No guarantee of FIFO. Some implementations are spin lock, some are blocking. It all depends. Okay. And in this case, going back to this example for a second, we can see that because this is not protected, when we try to count to 10,000, right, when we try to count to 20,000, I'm sorry, we end up with something less. We're losing updates. Some of these updates, you're incrementing and you're incrementing, but you're incrementing the same value. You both count 5 to 6, and now store that 6. Okay. So now these should be incrementing 10,000 each. Somehow only 13,000 increments are happening, at least visibly happening. Okay. I told you earlier about this. When I look at that plus plus count, it's a move, an increment, and a move. A load, an increment, and a store. Key idea, in general, any sequentially consistent interleaving is possible, but some give an unexpected result. What the heck does that mean? Huh. Sequentially consistent interleaving. What does that mean? Well, that basically means that it's possible for these things to interleave any way the scheduler can interleave them. But just because the scheduler can do it doesn't mean the results are going to be right. If the scheduler interrupts something after it loads a value and before that increment is written back, there's going to be a problem. and we want to pay attention to are these operations that form the critical sections, the loads, the updates, and the stores, the loads, the updates, and the stores. Critical sections because they manipulate the critical resource, or a critical resource, in this case a critical variable. Here you can see my load, update, store is interrupted by a load. Oops. This load and this load are concurrent. They're reading the same value. Unfortunately, this load's going to update and store, and this one's going to update and store. They both didn't update, but they both updated to the same value. Here we have another problem, right? Load, load. This one updates and stores. Here, these three are still together, but this load, update, store sequence is interrupted. Sadly, by something else that loads, updates, and stores. Oopsie. Okay. Here's the head, code we don't care about. It comes before the stuff we care about. Here's the tail, code we don't care about because it comes after the stuff we care about. Here's the critical section, the load, the update, and the store. So this is thread 1. Thread 2's head, its critical section, load, update, store, its tail. If we trace the progress of a process, here's thread. Here's thread 1 executing its head, then its load, then its update. Now it's getting interrupted and thread 2 is making its progress. Thread 2 is executing its head and now its load. Now we've got a problem. Both of these processes have loaded variables, right? They both are thinking 5. Now this one does its store. Okay, so it's writing out 6. And then the tail. And this one does its update going from 5 to 6. And then storing it, stores a 6, and then the tail. So now we have a problem. So we refer to this area as the unsafe region, right? Because once I do the load, I have to proceed through until I do the store. If I get interrupted by another load, there's a problem. Or by another update, there's a problem, right? So if I start here, I can't go up until I get to here. If I start here, I have to continue this way until I get past that store. Right? If thread 1 starts the load, it has to finish the update in the store before thread 2 can run. If thread 2, however, finishes the load, starts the load, it has to finish that update in store before thread 1 can run. So it has to be here or it has to be here. But we can't be manipulating this space because that means that we're past the load and past the load. Oops. Make sense? So you can see a safe trajectory is an interleaving, process 1, process 2, process 1, process 2, right? Some mixture there that doesn't get into that unsafe region, that doesn't result in an interrupted critical section. An unsafe interleaving is one that does. How can we guarantee a safe trajectory? How can we guarantee that a load, update, store sequence, or whatever our critical section happens to be, will not be interrupted? The answer is we need to synchronize the use of these two things. We need to coordinate. We need to make sure they're not going to interrupt each other. Most common way of doing this is a mutual exclusion policy. We're going to structure our code such that it's not possible. The use by one excludes the use by the rest. Sort of the classic semantics for this are mutex initial init, mutex acquire, mutex release. You initialize the mutex before you spawn your threads. When you approach the critical section, you acquire the mutex. When you're done with the critical section, you release the mutex. If you acquire the mutex and it isn't ready yet, you're not going to know. You're just going to block until it is. And then when it's ready, you'll get it and continue. Now, semaphores are another abstraction, another synchronization tool. Okay? Semaphores count resources. All right? Don't worry about the slide yet. Don't read the slide. If you're focusing on that, you're going to miss part of the story. Okay? So a mutual exclusion policy is good enough if there's only one instance of the resource. It's not good enough if, for example, there are more instances of the resource. As a for example. So think about the average bathroom. There are multiple toilets, right? It's okay for 5 people to be in the bathroom at a time. But it's not going to work if there are 5 toilets and 10 people in there, right? So mutual exclusion isn't the policy we want. We don't want a policy that says 1 bathroom, 1 person if there are 10 toilets. We want a policy that says, 10 toilets, 10 people. So if we have a pool of these resources, and they're all equivalent, I mean, you may have your favorite toilet, but in a pinch they'll all do. Okay? If we have a pool of these resources, we want to manage them that way. We want to have a policy that says not more than 10 users, or not more than 5 users, or not more than 3 users, whatever it happens to be. So to do that, we don't want mutual exclusion. We want a policy of not more than. So semaphores allow us to do that. We initialize the semaphore to the number of available instances. There are 5 toilets, there are 10 toilets, there are 3 toilets, whatever there are. And then we have 2 basic operations, traditionally known or classically known as P and V. Okay? I don't speak Dutch, I'll terribly mispronounce the words, but P and V come from Dutch words. Okay? Proberen, Verhogen, perhaps. Okay? I think proberen means to test or to look, and Verhogen means increment or add. That's what people who know these things tell me. Okay? So here's how it works. Pun intended. When I approach the bathroom, I call P. Ha ha ha. That was funny. You got it. Okay, so when I approach the bathroom, I call P. P does this. If there are available instances of the resource, the count goes down, and I proceed. Does that make sense? If I'm looking for a toilet and there's one available, the count of available toilets goes down, and I proceed, and I'm able to use the toilet. If there are none available, I block. Okay? Does that make sense? V increments the count of available resources. So I approach the bathroom, I do a P until I get a toilet, I make use of the toilet, and then I do a V, releasing the toilet. Make sense? Do you see how that works? So the semaphore variable models the number of available resources. 5 toilets, 4 toilets, 3 toilets, 2 toilets, 1 toilet, 0 toilets. Can a semaphore variable ever be negative? No. We never have a negative number of toilets. You block if there are not enough. And then proceed when you can safely do that. Now the only operations on a semaphore are initialize P and V. There is no peak operation. You cannot look into the semaphore variable and see the count. You can initialize it. You can call P if you want the instance of the resource. You can call V if you want to release an instance of that critical resource. But you cannot know how many are available or not. And this is a critically important point. And it's not on the slide, so make mental note of it. You cannot peek and see the value of a semaphore. You will never find that operation. The operations are init, P, and V. That's it. Now, that's not just because that's the way it was created. There's a really good reason for that. What's broken about a peak operation on a semaphore? Why could that never really work? What's that?
What happens if it would happen if two people look at the same time and they both see that it's open and they're like, oh, we can go in.
Yeah. What happens if we both peak, say, toilet, race, crash? Right? You can't do anything with it because as soon as you get the value, it could have changed. Your information can be stale the moment you get it. You might as well just pick a random value. I think there are 6 available. It could be more or less. Between the time you read that value and the time you use it, resources could have become available, resources could have gone away. Whatever you have is just stale to the point of meaningless. It might not even be close. Okay? So what we show here within brackets is that in order to implement a P, we're probably doing something like this. Okay? As long as the count of available resources is 0, wait. Once the count of available resources is not 0, decrement the count and keep going. The brackets suggest this is atomic. In other words, not interruptible. So the semaphore basically guarantees the semantics that we test for, that we somehow wait until we get until a resource is available, and then we safely decrement the count and then proceed. Okay? Somehow by magic. This is guaranteed to be uninterruptible. As if uninterruptible, atomic. Okay? This is guaranteed by the operating system if you're talking about inter-process communication. Okay? Semaphores that can be shared among processes. This is guaranteed by the thread scheduler if you're talking about semaphores that exist between threads. Okay. The invariant is that the count of available resources can never be less than 0. It must always be greater than or equal to 0. Only 3 operations we have: init, p, and v. Now, in the POSIX threads library, the operation traditionally known as p is known as wait. In the POSIX threads library, the operation traditionally known as v is known as post. Post oftentimes meaning update. I'm going to post that change. I'm going to post your grades. Okay? This confuses people because people see sem_post and think that's p. Or they associate p with post in some way. So no, this is just different nomenclature. What's traditionally known as a p is in the library known as a wait. What's traditionally known as v is in the library known as post. So your book kindly has given you wrappers so you can use p and v, which align with sem wait and sem post. Okay. Now, we're a little confused in the way we present this next idea, I think. All right? Mutex is one abstraction. A semaphore is another abstraction. Mutual exclusion is a policy of at most one user. You have the mutex, you've acquired it, or you give up the mutex, you've released it. The mutex is available or the mutex is not. Does that make sense? Now, instead of having mutexes, I can also have semaphores. I can say I have one instance of the resource available. And then I acquire that resource by doing a semp, and I release that resource by doing a semv. Does that make sense? So we call a binary semaphore, a semaphore whose value alternates between 1 and 0, can be used to implement mutual exclusion. Does that make sense? So I can use a semaphore to implement a policy of mutual exclusion. but it's actually, in an abstract way, doing something different. It's counting the number of available resources between 0 and 1. So a lot of people go through 213 and think that semaphores and mutexes are the same, but they're different. That mutexes, 0 means locked. Mutexes, 1 means locked and 0 means unlocked. And semaphores, 1 means available and 0 means locked. That's not correct in either case. Okay? It is in fact true that if I initialize a mutex to 1, it's locked. Okay? And if I initialize a semaphore to 0, it's locked. And when I release a mutex, it becomes 0. And when I release something with the semaphore, it goes from 0 to 1. So it is true that one goes between 0 and 1, and one goes between 1 and 0. They're opposites. But you shouldn't worry about that. That's a very bad way of thinking about it. That's an evil way of thinking about it. It'll confuse you in the long run. You should realize that in mutexes, the semantics are acquire the mutex or release the mutex. I am holding the mutex or I am not. And that with semaphores, you're counting the number of available resources. Indeed, it's true that you can't access a resource if you're not 0 holding the mutex. Right? So, but don't worry about that. Think about this in terms of what it is. See, here, this slide bothers me because we've named a semaphore mutex. And in fact, we are using the semaphore to implement mutual exclusion. We are. But we're doing it by counting available resources. We initialize this semaphore to 1. This says mutex equals 1. Ah! No! That works in this slide and this slide only. The proper way to think of this is 1 resource is available. Therefore, I'm initializing my semaphore to 1 to model 1 available resource. Does that make sense? Okay. Now, here, I acquire the 1 available resource, making there 0 available resources. I execute my critical section, and then I release the instance I acquired, taking it from 0 available to 1 available. Does that make sense? So now if I come in and I do this P and take the available resource, and then I'm blocked, and someone else comes in and does this P, there are no resources available for them. So they wait. And then eventually it's my turn again. I execute the critical section, and eventually I have enough turns to get to the point where I release that resource. The number of available resources becomes 1. Eventually the waiting thread gets to run. It's in this P, finds the resource available, and then continues. Okay? Threads model resources. Okay. So what is this? Well, user time, system time, and clock time is if you had a stopwatch and we're measuring it. Okay. The bottom line is this. When we start to do synchronization, things run slower. We're doing more work. We're spinning waiting for a resource. That spinning is taking up processor time. That processor time is time the other thread that could be doing work could be working. So we're wasting time acquiring resources, releasing resources, and spinning doing nothing while waiting for resources. Or we're wasting time blocking something and unblocking something. So adding synchronization slows down our code. Of course, as one of my bosses once told me, if I wanted the wrong results, I could make it run much faster. I think I told you guys the story of the neural network that wasn't converging. Right? So we don't synchronize every variable in our code because it's unnecessary, it would slow things down. We synchronize the critical sections, right, to protect the critical resources. Now, there is a difference in the cost, at least typically, between a general purpose semaphore and a simple mutex. If you're dealing with a primitive that's actually called a mutex, it's only correct when bounced between 0 and 1. Okay, mutex acquired, a mutex released. Somebody has it, and or no one does. And so mutexes generally involve less overhead than full-blown semaphores, which have the ability to protect resources where there can be more than one instance. So here you can see that we've added into this the P's and the V's, the P's and the V's. And so once I acquire my resource here, the other thread cannot. Or if this thread acquires the resource, the other thread cannot. And so now, once I proceed past this point, it's impossible to get into the so-called forbidden region. Because the other thread is stuck waiting for the resource. We're now guaranteed to be safe. So in order to deal with code that's running concurrently, programmers need a clear model of how variables are shared by threads. That model actually is nuanced. We need to understand what the high-level model is, and we also need to understand the actual model for when that breaks down and we have to debug. It's one thing to understand each thread has its own call stack, and each thread operates independently, and blah, blah, blah. That's great. We also need to understand the nuance that they all share the same process, they all share the same virtual memory, and so there's no protection. Thus, one can pollute another. Hopefully, we don't need to know that very often, right? But it'll turn out to be useful debugging. Variables shared by multiple threads must be protected to ensure mutual exclusive access. Okay. What does that mean? Well, more generally, that means if we identify a critical resource, something that's being shared that can't safely be shared, we need to protect it so it's not. That critical resource can be some critical variable, for which I want a mutual exclusive policy. It might be access to some hardware device where the queue can't be more than 5. Okay. Regardless, we need to identify what is the nature of that resource. How can it be shared? Not more than 1 user, not more than 2 users, not more than 3 users, what is it? And then we need to have some mechanism for enforcing that policy. Mutexes are a fundamental mechanism for enforcing mutual exclusion. Semaphores are a fundamental resource for enforcing at most n policies, where at most one is one such policy, right? At most one user. Okay. And we talked our way through threads versus processes before. We talked our way through the pthreads interface before, right? We talked about that, pthread create. You guys are looking at me a little funny? How many people remember this? Raise your hand. How many people do not remember this? Okay, fair enough. We'll talk through it. So pthread create is the equivalent of a fork. It creates a new thread. Okay? It creates it within the same process as whatever's calling it. With processes, you have a hierarchy, a parent and a child. With threads, all threads are peers. There's no parent-child relationship. They're all siblings. Okay? Pthread join is sort of the equivalent of a wait. It lets you collect the status from another thread. Pthread self gives you your own thread ID. Okay? Pthread exit is the equivalent of exit, but it exits a thread. Pthread cancel kills a thread. It's the equivalent of a kill. Return is just like any other return. If you return out of the thread's body, it exits the thread. Exit exits the process, which ends all threads. Here's the example. I think we saw this last class. We create a thread. We wait for the thread to finish with a join. We pass in the function that's the body of the thread, and it runs. We get back a thread ID that's passed by reference. We create a thread ID variable, and we pass in its address. It has to be allocated, right? We have to pass it the address of an actual, pthread underscore t. It can't be a pointer to nowhere. Okay. Threads take one argument, nominally of type void star. It can be a pointer to a struct. So if I want my thread body to take 10 arguments, I just create a struct that has those 10 arguments. I populate the struct, I pass the struct by reference. I get in here, I dereference the pointer. If I want my thing to take just one variable, an int, I could nominally create a struct that has one variable, an int. But more commonly, all I do is cast my pointer to an integer and send it that way. Make sense? Yeah?
If we create a thread, then join it, then create another thread, and then join it, does that mean we've effectively made it sequential because the program will wait for the first thread to complete before it does the second one?
Absolutely. I mean, if you have three threads, your main thread, thread 1 and thread 2, and you're in a situation where the main thread exists first, then you spawn thread 1, then you wait for thread 1, and then you spawn thread 2, and then you wait for thread 2. At most, the concurrency is between the main thread and thread 1 or thread 2. Thread 1 and thread 2 run sequentially. And because thread 1, the main thread is doing the waiting, it also runs sequentially. Right? The only concurrency you might have is that you could actually have, for a small amount of time, concurrency where thread 1 is running before the main thread calls wait, or thread 2 is running before the main thread calls wait. But for the most part, it's going to be sequential, where it's going to be main thread, thread 1, main thread, thread 2, main thread.
So for a multi-thread program, you would see multiple creates and then multiple joins come after the.
That's correct. If we're doing some type of program, we intend for these threads to run concurrently, we'll let them run concurrently and wait for them all at the end, if at all. Okay. Any other questions? All right. Have a great day, everybody.